Okay, today we're going to look at the combined gas law and Dalton's law of partial pressure. This is going to encompass 4 gas laws, of which really you kind of only need to know 2 of them, and they're not terribly difficult. So let's go ahead and get started. So this is the combined gas law. I want to show you the combined gas law first before we talk about the 3 laws that make up the combined gas law. So P1V1 over T1 equals P2V2 over T2. As you'll see, it's called the combined gas law because it's a combination of 3 other gas laws. You really only need to use this equation or memorize this equation, because if there's something, for instance, that you don't need, you can actually cross it out. So if you know that temperature is being held constant, you can cross temperature out of the equation, and you get our first law that we'll look at here, which is Boyle's law. So again, combined gas law, if you memorize that, you should be pretty good for most of the gas laws unit. So let's start here with Boyle's law. Just as a little bit of background, Boyle's law works. He looked at a J tube, and so he looked at the pressure and the volume of the gas and was able to set up a relationship between them by looking at the height of the mercury. That's how he measured the pressure, right? And then he could look here and see the volume. Not super important how he did it, but just that if he kept the temperature constant, he found a relationship between pressure and volume, or Boyle's law here, P1V1 equals P2V2. This is what it looks like if it's graphed. It is important that you understand what the graphs of each of these laws looks like. So Boyle's law, you can see here it's inversely proportional. If one is going up, the other is going down, and it does go down in a curve. So if it shows up in a question, you do need to be able to recognize what Boyle's law looks like. So practice number 1, I'll give you a second and allow you to practice it. I want to make sure we get through all of these laws, so I'll have you practice it and then check with a neighbor. We are not going to go through it right now. I will say this, however, as you're reading through a question, what I want you to do is I want you to sort of dictate the question or annotate the question before you plug anything into an equation. So, for instance, if I'm looking through this, I know that I've got that's a volume, I have a pressure and another pressure. So I know right away sort of like what my variables are before I start working out my problem. The second gas law here is Charles' law. So Charles' law is looking at the directly proportional relationship between volume and temperature, assuming that pressure is held constant. And then you can see here at the top, he did a lot of work with gases, created the first hot air balloon with hydrogen gas, and did that first solo flight. So he's cool in that sense. But you are always relating volume and temperature in Kelvin. And this is super important. Kelvin is always in the positive scale. That's one of the reasons why we use it. But make sure all of your temperatures are converted to Kelvin. Charles' law looks like this. It's directly proportional. The one thing that is significant about Charles' law is that all of our graphs can be extrapolated out to 0. So if you see here, these solid lines indicate where data was collected, and then the dotted lines here are the extrapolation out to 0 degrees Kelvin. And then here again, we're looking at volume versus temperature as a molecular view. Notice that I've got high kinetic energy here. You can see that as the particles are moving, it's trying to illustrate that in the image here, as opposed to when I cool it, the energy of my particles slows down, and so my volume becomes smaller. It shrinks my balloon because I don't I'm not able to push on the sides of the balloon as much as I did with high kinetic energy. Again, here's another set of practice. Go ahead and try it out, and then check it out with your neighbor. Notice that my temperatures here are in Celsius. You will have to convert those to Kelvin. Our third law here is Gay-Lussac's law, and that's looking at pressure versus temperature. It's the same idea. You should have 3 of these 4 variables. You plug it in and you solve for your unknown. And these 3 laws combine, these make our combined gas law. Again, if you don't need something, or if something's held constant, you can just remove that variable from your equation, which makes it super simple. So, this gas law may be new to you. It's Dalton's law of partial pressure, and it's pretty simple in that the total pressure in a container is just the sum of all of the pressures. So if I had 2 atmospheres of pressure coming from N2 and 3 atmospheres of pressure coming from H2, then within my container, P total is 5 atmospheres. So super simple, you just add them all up. Okay? You will come across this. It's called the mole fraction. The mole fraction is just the ratio of the number of moles of one particular atom over the total number. So it would be like N number of moles of A over number of moles total. So if I was looking for the mole fraction of H2, that'd be the moles of H2 over moles total. Okay, so not hard, don't make it complicated. If I know that I have 10 moles total, and I have 2 moles of H2, right, then my mole fraction here is 0.2. Okay. Right, there you go. If you are looking at pressures, you can extend this out in calculations that my mole fraction here is the like my moles of A over my moles total can then be extended out to the pressure of A over pressure total. Right, so you can pull that out there. And that makes things really, really, really easy if you know what the mole fraction is. Okay. Here's another practice problem. Try it with your neighbor and then check. And here you go. Here's your mole fraction. And then I can calculate the partial pressure if I go backwards from this. So if I have my mole fraction and I know my total pressure, then I can go ahead and calculate the partial pressure for thing A. Here's a 4th practice problem. Try it out, check with your neighbor. Okay, on your equation sheet, here's Dalton's law of partial pressure for you. Here's the ideal gas law, which we'll talk about tomorrow. And here's your mole fraction right here. Okay, you can rearrange that however you need to, but it gives you, if you are looking for the partial pressure of thing A, it's P total times your mole fraction. So that's on your equation sheet. You don't need to memorize that. Just go to your equation sheet and find it. Here's another practice problem for you. This one will take you a little bit longer, so try it out and then check with your neighbor. Okay, I will see you tomorrow.